I will begin my discussion of electric flux through a closed surface and Gauss's law by a simple example of trying to find the electric flux through a closed surface, namely the surface of the cube pictured here of side 1. Electric fields can be very complicated. The most general expression can have all three functions of x, y, and z, and the x component, y component, and z component themselves can be different functions of x, y, and z. The example I'm choosing is a much simplified version of the most general possible electric field. The x component is 3x squared, the y component is 4x squared z, and the z component is 5 times y. We have to take this electric field and find the flux through the surface. Now, if you want to think about the flux in a physical way, you can think of a fisherman putting a net inside a pond and finding out at the end of the day how much fish he or she has caught. So the electric field can be thought of as little fish darting around the pond. Okay, so we have to find out what the net catch of this fisherman is. The catch is measured by the concept called electric flux, and the flux is given as follows. The electric flux through a closed surface denoted by phi sub e superscript c is the oriented surface integral, and that circle with a arrow means it's an oriented surface integral over the surface, in this case the surface of the cube, of the electric field dotted with the area vector on the cube. There are 6 area vectors on this cube. I will denote them by dA right, dA left, dA top, dA down, dA front, and dA back. It's not too hard to write actual vector expressions for all these dA vectors, which I will do next. dA left is just going to be, because it's on the surface with x and z coordinates, it's just going to be dx dz times negative j hat, because it's in the minus y direction. dAr, once you write one expression, the other one can be written almost immediately. The opposite vector can be written almost immediately by just removing this minus sign and substituting a plus sign. So let's repeat this performance for dA top next. dA top is going to have coordinates x and y, so it's dx dy in the direction z, so that's k hat, and dA down will then be the opposite of that, which is negative dx dy k hat. And lastly, we have dA front and dA back. So dA front, now the front and back surfaces are in the yz plane, so that's going to be dy dz in the x, which is I hat, and dA back is the same thing but in the negative I hat direction. Once you've written all these dA vectors, you just then have to split this up into 6 integrals and do each one to find the flux. Now, don't be too worried. I have pre-arranged this to only have one contribution, and that is in the flux through the front surfaces. So let's try this. Once you split the double integral into pieces, you're not going to put the closed sign anymore. Closed means the entire cube, and this means each face of the cube. So the front face of the cube times, remember dA front is the I hat. So when I take the dot product, the only term that will survive is the x component and the I hat component. So this is going to be E sub x times dA front without the I hat plus the integral on the back of the x component at the front location. This is at the front location. Here x component at the back location times dA back, and then I'll have terms for the other sides. Let me do left. Left will involve the y component, so that's going to be EY evaluated at the left side times dA left plus right, which would be EY evaluated on the right side times dA right, and then two more terms which would be top and down. Tops and downs refer to the k component, so it's EZ evaluated at the top side times dA top plus down EZ evaluated on the downside dA down. Now we just have to write these integrals out one by one. So this is just a very routine procedure. Ex is 3x squared. Evaluated at the front surface means evaluated at x equals 1. So 3x squared evaluated at x equals 1 is just 3. So that's going to be 3 times dAf, which is dy dz. Now the limits of all these integrals are from 0 to 1. Each of these integrals goes from 0 to 1 on the respective variables. For example, this integral is dy from 0 to 1. That integral is dz from 0 to 1. To avoid writing it twice, I'll just put a big fat 0 and a big 1. What about the back surface? On the back surface, which means x equals 0, Ex is 0 because it's 3x squared. So that's just 0. Very nice. That integral is easy. Let's do the next integral. E left, Ey. Ey is 4x squared z. And the left side is at y equals 0. Well, you're out of luck. Y equals 0 does not occur there. So you have to do a full-blown integral, 0 to 1, big 0 to big 1, of 4x squared z times dAl, which is negative dx dz. Because you look at the dAl there, it's got a negative sign. We don't have to worry about doing this integral. You can actually do it if you want, or put it in Wolfram alpha, or do the double integral if you like. But you don't have to. I'll tell you why soon. Let's look at the other integral. That one's going to be the same integral on the right side. Now Ey x squared z on the right side still does not depend on y. So it's still going to remain as 4x squared z. But on the right side, dAr is dx dz. Big 0 to big 1. And now you see why you did not have to worry about doing this integral, because they simply cancel out. And you can expect cancellations here too. Let's try this out. So this would be integral big 0 to big 1. Ez is 5y. At the top, it remains phi y. At the bottom, also it remains phi y. So that's going to be phi y. The top integral involves dx dy. And the bottom integral is the same thing, big 0 to big 1, phi y, but with a minus dx dy. So these two integrals also cancel out. The only serious integral that needs to be done is the first integral. Fortunately for us, that's a very simple integral. Like 3 can be taken outside. The integral of dy is just y between limits 0 and 1, so that's just 1. And the integral of dz is just z between limits 0 and 1, so that's also 1. So the answer is 3. The answer for the flux is 3. Gauss's law is an amazing law of nature, and it gives us the relationship between the flux, how much you catch, how much of this flux you catch in your net, and what kind of charge you have in that net. So it's as though without looking into the net, you can say what kind of fish you caught. Gauss's law says the following: the closed flux is equal to the charge enclosed divided by epsilon naught. I have introduced epsilon naught earlier in week 2. If Coulomb's law, F electric, can be written as k q1 q2 over r squared in magnitude, epsilon naught is related to the Coulomb constant k as follows. Coulomb constant k is 1 over 4 pi epsilon naught. So the value of the Coulomb constant, as you know by now, is 9 times 10 to the 9 Newton meter squared per Coulomb squared. So epsilon naught can be worked out from that. If you work this out, epsilon naught is going to be something like 8.85 times 10 to the minus 12, and the units are going to be the reciprocal units of k, which don't really look good at this point, but later on we'll have far better units to give epsilon naught. In week 4, towards the end of week 4, I will give you some much better looking units for epsilon naught. But right now, let's just take the units to be those of 1 over k. So that's just a number. It's a number, it's a constant of nature, and there are experiments to measure it. What Gauss's law tells you is that the enclosed charge can be found once you find the closed flux. So the answer to how much fish you've caught is really this. The enclosed charge, and the answer will be in coulombs. So it's 3 times epsilon naught. So I can basically do 8.9 times 3. So 9 3s are 27. So this will be something like 27 times 10 to the minus 12 coulombs, or 27 pico coulombs, because pico is 10 to the minus 12. In this manner, I've found out how much charge there has to be in the cube by simply working out the contributions of the electric flux on each surface of the cube. It's pretty remarkable that information on each surface of the cube gives you how much charge there is inside. It's as though you put the net inside the river and just look at photograph those surfaces and see how much fish are darting in and out. And into some surfaces you'll find more fish coming in than going out, and other surfaces you'll find equal number of fish coming in and out. These two surfaces that cancel, surface contributions that cancel, are those fish that simply come in the one surface and exit the opposite surface. Same thing with the fish in the z direction. They just go in and in one surface and come out the other surface. The only fish that get different counts is in these two terms, in the front and the back. you'll find that no fish are coming in from the back, but fish are coming out the front, which means that there must be some net catch. So that's roughly what's going on here.